everyone. Myself Rakhi Kumari, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the series of optical communication lectures, I am going to deliver before you overall fiber dispersion and polarization. In the previous 2 or 3 lectures, we are going through the process of dispersion. So, again I am repeating the dispersion in a single line, that is, a dispersion is a process in which pulse broadening takes place. That means, pulse get broadened as it is emitted from the input terminals, moves towards the optical fiber and reaches the receiver section. So, whatever be the pulse, exact pulse width at the input section does not remain same as at the receiver input, it get broadened, and this due to this broadening process, what is going to happen is that our adjacent pulse, that is neighboring pulse, get overlap with each other, and we face the problem of intersymbol interference, which is represented as ISI, intersymbol interference. And in this particular case, pulses are indistinguishable, that we can't able to distinguish between the signals which is transmitted from the input end. So, this is the dispersion, and when we talk about the dispersion, we have to include both intramodal dispersion are basically of the two type, that is intramodal dispersion and the intermodal dispersion. About that which we have already discussed in the previous lecture. So, when we are talking about the total or overall fiber dispersion, it should include both intermodal and the intramodal dispersion. The overall dispersion in multimode fiber is equal to both intramodal and the intermodal terms. It will be the summation of that one. So, and we know that the dispersion is represented in the form of pulse broadening, that is RMS pulse broadening. So, this is a sigma t representing the total RMS pulse broadening, and that is equal to sigma c square plus sigma n square. So, what is the sigma c? Sigma c is our intermodal or chromatic broadening, which is equal which is due to the intramodal dispersion, and the sigma n is the intermodal dispersion. And when we take this square of both and then we will take a root of that, we will get the total RMS pulse broadening. When we know that intramodal dispersion is basically of the two type, that is waveguide dispersion and the material dispersion. So, whenever we include the sigma c, that is our intramodal dispersion, should include both waveguide dispersion and the material based dispersion. But since the waveguide dispersion is generally negligible compared with the material dispersion in multimode fiber, this waveguide dispersion is negligible as compared to the material dispersion. So, sigma c can be written as the sigma m. We can write the sigma c equivalent to the sigma m, since in multimode step index fiber, multimode fibers, this waveguide dispersion is negligible. So, the overall intramodal dispersion can be represented with the material dispersion. Now, a overall fiber dispersion in a single mode fiber. We have talked about the multimode one, where the total dispersion should be equivalent to intramodal plus intermodal. Intramodal should comprise of both waveguide dispersion and the material dispersion, but in multimode waveguide dispersion is negligible as compared to the material dispersion. So, total intramodal dispersion can be equivalent to the material dispersion in the case of multimode fibers. Now, in the case of a single mode fiber, what will be the total or overall fiber dispersion? The pulse broadening in a single mode fiber result almost entirely from the chromatic or the intramodal dispersion. So, total dispersion, whenever we talk about the total dispersion, it should include both the intramodal and the intermodal dispersion. But as we know that intermodal dispersion exists due to the delay difference between the different types of rays propagating inside a waveguide. But in the case of a single mode fiber, only one mode is propagating. So, their intermodal dispersion is almost negligible or it is equivalent to 0 in the case of a single mode fiber, since only one mode is allowed to propagate. So, the chances of delay difference is negligible in the case of single mode fiber. So, in the single mode fiber, the total dispersion is mainly due to the chromatic, mainly we can say entirely due to the intramodal or the chromatic dispersion, as only single mode is allowed to propagate. So, there is a chances of intermodal dispersion is entirely nil. The bandwidth is limited by the finite spectral width of the source. So, this finite spectral width which is given by the source itself, that is due to LED or laser. LED or laser having the different, or within the LED also we have a different finite spectral width that decide the bandwidth of this particular dispersion. The transit time or the specific group delay, which is represented by tau g, for a light pulse propagating along a unit length of a single mode fiber is given by tau g should be equal to 1 by c d beta upon dk. So, the total first order dispersion parameter or the chromatic dispersion of a single mode fiber, first order, it is equal to dt and it is equal to d tau g upon d lambda, and we know the value of tau g and we have to just differentiate over here. And we know beta is equal to 2 pi by lambda. So, you have to substitute 2 pi by lambda here, then only you can differentiate it with the help of lambda. So, when we are trying to differentiate it, always try to keep in mind that we have to substitute this beta with 2 pi by lambda and then we will get this result, and omega is equal to 2 pi f. You can solve it and get this result. So, tau g value you can have this from here and substitute, and you will get the first order dispersion parameter or the chromatic dispersion of a single mode fiber. The fiber exhibit intramodal dispersion when beta varies non-linearly with the wavelength. Exactly, this is a property of a intramodal dispersion where beta has to be vary non-linearly because with the wavelength. The RMS pulse broadening caused by chromatic dispersion down a fiber of length L is given by the derivative of the group delay with respect to wavelength, and it is given by this one. This is the RMS spectral width given by the source. L is the length, tau g group delay. So, total RMS pulse broadening, it is given by this, and since we have in intramodal dispersion we have material dispersion as well as the waveguide dispersion, and material dispersion parameter is given by this lambda by c d square n upon d lambda square, where n will be equal to n1 or n2, and it depends upon the whether we are considering the core or the cladding. This is the material dispersion parameter. And next one, that the waveguide dispersion parameter, that is equal to minus n1 minus n2 lambda c. We know the V number, that is normalized frequency, d square Vb by dV square. But these are the several types of dispersion which exist in a single mode fiber. So, if we want to have the dispersion is not at all beneficial for any fiber, optical fiber communication. So, for that purpose or just for the minimizing or for reducing, we have to take the multiple number of steps. So, dispersion modified single mode fiber. This, what does this mean? As this term itself indicates कि हम dispersion, we are modifying the dispersion in a single mode fiber. And what will be the application? What is the importance of this modification? Just for reducing the single dispersion which exists in the single mode fiber. It is possible to modify the dispersion characteristic of a single mode fiber by tailoring of specific fiber parameter, and this can only be done when we tailoring. What does it mean? Ki something we add, something we subtract, and with this by adding or subtracting some parameters. So, by making changes in the some parameters, we can have the dispersion modified single mode fiber. So, however, the major trade-off which occur in this process between material dispersion and the waveguide dispersion. In a single mode fiber, only intramodal dispersion exists, which comprises of waveguide dispersion and the material dispersion. So, total dispersion will be equal to material dispersion parameter and the waveguide dispersion parameter. So, when we add on this, we get this expression, and since these two components works in the opposite direction, this is the major reason that we can have able to modify, because we can reduce it to 0 or to the minimum value, since there exists a minus sign between the dm and dw, which is the material dispersion parameter and the waveguide dispersion. So, at the wavelength longer than ZMD, zero material dispersion point in the most common fiber design, the dm and dw components are of opposite sign at which particular point? J and D, and therefore can be made cancel at some longer wavelength, and this is possible only at the longer wavelength. We can have the material dispersion and the waveguide dispersion have the opposite sign, and there is a possibility to cancel each of them and make it the value of 0, so that to obtain a material having a 0 dispersion. Hence, the wavelength of a 0 order chromatic dispersion can be shifted to the lowest loss wavelength for the silicate glass fiber at. So, for the silicate glass fiber, this can be possible at 1.55 micrometer to provide both low loss dispersion and the low loss fiber. If we are going to reduce it, we are getting the low loss fiber, a low dispersion fiber, and this is an example, that is for the silicate glass fiber we can obtain at this 1.55 micrometer. This can be achieved by such mechanism as a reduction in the fiber core diameter. So, what you can done? You can easily see that, of course, N1 is in, what is the N1? N1 is in numerator side. So, you can reduce the, if we want to, resultant should be reduced form. So, what we have to do? We have to reduce the components in the numerator portion and to increase the parameters at the denominator portion. That is why N1 has to reduction in the fiber core diameter. That means N1 which exists in the numerator side has to be reduced with an accompanying increase in the relative or fractional refractive difference, or that is why it is mentioned it is possible in the longer wavelength. Lambda is in denominator side. So, by changing some of the parameters at this level, we can have the reduced dispersion and we can obtain the dispersion shifted single mode fiber. But continuing this, an alternative modification of the dispersion characteristic of single mode fiber involve the achievement of a low dispersion window. That means, of course, window is dependent upon the wavelength, and if we are able to calculate the wavelength at which we can have the lowest dispersion, because in this wavelength term exists. So, we can able to achieve the low dispersion window over the low loss wavelength and region between this range 1.3 to 1.6 micrometer. Such fibers which relax the spectral requirement for optical source and allow flexible wavelength diffusion multiplexing are known as the dispersion flattened single mode fiber. In order to obtain DFFs, that is dispersion flattened single mode fiber, we have to make some changes as we have to for the dispersion shifted fibers. In order to obtain DFF, multi-layer index profile. So, what is the process to obtain the multi-layer DFFs, that is multi-layer index profile are fabricated with increased waveguide dispersion which is tailored to provide overall dispersion less than 2 picosecond per nanometer inverse kilometer inverse over the entire wavelength range of 1.3 to 1.6. So, for dispersion shifted, we have to make a change in the core refractive index and in the wavelength, and for the dispersion flattened, we have to use the multi-layer index profile fibers. In effect, this fiber exhibit two wavelength of 0 total chromatic dispersion. In generally, this fiber exhibit two wavelength of a 0 total chromatic dispersion, and the chromatic dispersion is the only form of dispersion which is exist in the single mode fiber. Now comes the polarization. As we know, polarization is what? Polarization is the process. In the layman term, we can say if we used to provide a direction to any ray, then that ray is said to be polarized, and in the polarization case, that particular ray has bound to move in that particular direction which is already provided to that, and this polarization does not exist for the long distance in the case of a optical fiber. So, we have to make some changes so that polarization can be maintained, because since if polarization gets distorted, that means direction of a rays get distorted, and if the direction of the rays get distorted, what happen? What is going to be happen? It will not reach the destination, it will not reach the proper destination which is allotted to it. So, polarization plays a very important role. So, now cylindrical optical fiber do not generally maintain the polarization state of the light input for more than a few meters. Cylindrical fiber does not maintain the polarization more than a few meters, and hence many application involved. So, many problems arise, one it is mentioned, but many problems arises. The major one is mentioned here. Many application involving optical fiber transmission, some form of intensity modulation of the optical source is utilized. Nevertheless, system and application have been investigated which could require the polarization of course, polarization state has to be maintained over a significant distance, and thus the fiber has been designed for this purpose. But as we already all of us know that polarization state has to be maintained, which is not followed in the case of cylindrical fiber. So, for maintaining this polarization state, some sort of fibers has been designed. Similarly, as the for reducing the dispersion, we have designed the dispersion shifted fibers and the dispersion flattened fibers. Similarly, for maintaining the polarization, we have designed a special type of fibers, that is this one. This fiber are single mode. So, what will the characteristic of the fiber which are designed for this maintaining the polarization? This fiber are single mode and maintenance of the polarization state is described in terms of phenomenon known as fiber birefringes. The fiber which is designed has a single mode and the phenomenon which are described, which are describing the maintenance of the polarization is called the fiber birefringes. Now, so we are going to start the fiber birefringes. Single mode fiber with nominal circular symmetry about the core axis allow the propagation of two nearly degenerate mode with orthogonal polarization. What is saying in this particular line? Just have a look. Okay, we have a single mode fiber with a nominal circular symmetry. Circular symmetry clearly indicates a circular structure in which if there exists a core two modes, that is first mode and the second mode, have two nearly degenerate modes. If we are talking about the degenerate mode, that means degenerate modes are those modes which have similar properties with orthogonal polarization. Orthogonal polarization means they have a 90-degree difference upon their polarization state. If one is travelling in the x, then other is travelling is in the y. So, it is talking about the circular symmetry. So, now can we say that circular symmetry always exists? But they are therefore bimodal supporting HX11, HEX11 and HEY11, that is one is in the x axis and one is in the y axis and both are same, HE11 and HE11, both modes are same HE11, but one exists in the x direction and the other exists in the y direction, where the principal axis x and y determine the symmetry element of the fiber cross section. Hence, in an optical fiber with an ideal optical circular symmetry core, both polarization modes are propagate with the identical velocity. That is why they are called as the degenerate mode, because they have a property similar properties. Both of these modes travel with the same velocity. Manufactured optical fibers, however, exist some birefringes resulting from difference in the core geometry, but as we fabricate, as we manufacture, this core geometry get distorted and it gets a elliptical, and when the elliptical, what will happen? In elliptical case, we can easily say this type of electrical, in that we can easily say that this two axis of the core varies, and if this are varying, that means the polarization state can't be maintained, resulting at the result from the variation in the internal and external stresses and the fiber bending, which is responsible for this internal and external stresses and the fiber bending. The fiber therefore behave as a birefringent medium due to the difference in the effective refractive index. Of course, refractive index effective will be changed and hence phase velocity, and this two orthogonally polarized. For this now also it is orthogonally polarized, but the properties now get changed and now it is not remain the same. The modes therefore have different propagation constant beta x and beta y, which are dictated by the anisotropy of the fiber cross section. In this case, beta x and beta y are the propagation constant for slow mode and the fast mode respectively. You can easily say beta x is this one, it has to travel the largest distance, so it is called the slow mode. Beta y in the y axis, and it has to travel the shortest distance, that is why it is called the fast mode, slow mode, fast mode. So, for circular symmetry it is okay, but when it get elliptical symmetry due to various reasons which occurs due to its manufacturing process. The fiber properties get distorted, and now we have a two modes having different propagation constant beta x and beta y. Due to different phase velocity, refractive index, various parameters are included in this. One mode is now fastest and one is slowest one. And when the fiber fluctuation independent of the fiber length L in the z direction, then the we are fiber length independent in the z direction, there is no connection with the z1. So, in that case modal bifringes, modal bifringe Bf is given by beta x, that is beta x what is what? The fastest slowest mode in the x direction, beta y fastest mode in y direction. So, modal bifringe Bf is given by beta x minus beta y upon 2 pi by lambda, where lambda is the optical wavelength. The light polarized along one of the principal axis will be retain its polarization for all L. The difference in the phase velocity, we have seen that there exists a difference in the phase velocity, and that is equal to phi z equal to beta x minus beta y into L, that is length of the fiber. The phase coherence of the two modes component achieved when the delay difference between the two transit time is less than the coherence time of the. So, how to achieve the phase coherence? It is given here, and this can be achieved when the delay difference of two transit time is less than the coherence time of the source. The coherence time of the source is equal to the reciprocal of the uncorrelated source frequency bandwidth, and that is called the coherence time of the source, and the phase coherence, that is should be less than the phase coherence time of the source, that is less than 1 by del f. So, based on this bifringent coherence is maintained. अब है कि up to what length this bifringent coherence is to be maintained. So, bifringent coherence is to maintain between C upon Bf, that is our modal bifringent, del f, this is frequency source frequency width. So, we can write this in this form, where C is the velocity of light and del is the source line width. When a phase coherence is maintained over the coherence length, leads to the polarization state which is generally elliptical, but which varies periodically along the fiber. The characteristic length Lb for this purpose corresponds to the propagation distance for the which a phase difference which a 2 pi phase difference accumulates between the two mode is known as the beat length, and it is given by Lb should be equal to lambda upon Bf. So, these are basically the phenomenon which decides up to what length the polarization can be maintained, and this enables the designer or manufacturer to design a fiber where the polarization state can be maintained. So, here we have the one numerical based on this modal bifringens. The beat length in a single mode optical fiber is 9 centimeter. So, what is given here? Lb, which is our beat length, is 9 centimeter. When a light from an injection laser, the source which is used here is the injection laser, have a spectral line width of 1 nanometer. So, what is the spectral line width? Del lambda. So, this is del lambda, and a peak wavelength of lambda 0.9 micrometer is launched into it. Determine the modal bifringe you have to calculate the BF, modal bifringe, and the coherence length, that is LBC, whose formula LBC and BF already given to you. In addition, calculate the difference between the propagation constant for the two orthogonal. The propagation constant beta x minus beta y, propagation constant for the two orthogonal में, and then you have to check the result also. So, now LB is equal to lambda upon BF. So, we can say that BF should be equal to lambda upon LB. Lambda value is given, that is 0.9 into the power minus 6, and LB is also given 9 centimeter. So, when we substitute, we get the value of BF, that is modal bifringes, and that is equal to 1 into 10 to the power of minus 5. Now, for calculating the coherence length, this formula can be used, lambda square BF into del F. Lambda value is already given to us, BF we have just calculated, and del F is also given. This is 1 del F, this is lambda, and BF we have calculated. So, LBC should be equal to lambda square upon BF into del F. We have substituted the value of lambda square, BF from this, and del F. We get the coherence length as 81 meter. Now, to calculate the propagation difference between the propagation constant, it can be calculated with the help of modal bifringe formula, which is equal to BF should be equal to beta x minus beta y into divided by 2 pi by lambda. So, beta x minus beta y should be equal to BF into 2 pi by lambda. So, we have used that formula only, BF into 2 pi by lambda. 2 pi BF value from the first part, this one, and lambda 0.9 to 10 to the power minus 6, and that is equal to 69.8. Now, we have to check the result also. So, for checking the result, we have to do what? We can use any of the formula which is given, and we have the get the value of the key. We have same value or not, and then we have propagation constant difference between the two orthogonal modes, which is beta x minus beta y. So, what we have done in the today's lecture, we have gone through the dispersion, sifted fiber, total dispersion which exists in the multimode and in the step and text fiber, and we have seen that polarization does not remain to the complete in the length of the fiber, it exists only for the few meters. So, how to maintain the polarization over a optimized length over a required length? So, for that modal bifringes phenomenon is followed, and we have done the numerical related to that only. So, you should revise that and also try to solve the numerical which is solved with in this lecture. Thank you for attending class.